Greetings. Today we're going to consider how to change variables. This is akin to substitution in single variable calculus. Now we have multiple variables, so things become a bit more complicated. Last time we already saw how to convert polar coordinates to the usual double integrals. And we saw that for spherical coordinates, perhaps we need to use complicated geometry in order to figure that out. Today we're going to see the general method that can bypass this complicated geometry. The setup is as follows. We are going to have a function g that transforms a point in some UV plane to a point in the XY plane. And I'm going to use polar coordinates as an example right now. But let me say that when we transform UV to XY, I will also use X and Y to denote the function, the name of the variable, and also the name of the function that compute its values. I think this actually makes things clear. Also, sometimes it will be convenient to think of the input-output as points and sometimes as vectors, and we'll just go back and forth. And if I use the wrong kind of angle brackets or pairs, it's all right. We'll figure things out, and I will be lenient with you as well. So here, as a first example, G is a map that converts polar coordinates r theta to rectangular coordinates x, y. We know this formula. Yeah, how do we calculate calculate x from r and theta? We have r cosine theta for x, and then y is r sine theta. And now I hope you can see why I write them as functions, because x is essentially a function of r and theta, and y is a function of r and theta as well. And g simply packages these two conversions into one. So here, g takes in two things and outputs two things. Let me draw a picture of what's going on. So here is, I'm going to draw it in the r theta plane. Just like here, I said it takes a point in the UV plane. Here are u and v are r and theta. And then we're going to map it using g. This is our map. And it's going to map over to the xy plane. Now, let's take a line r equals r1 that maps over, we know, to a circle of radius r1. If we take another line r2 that maps over to a bigger circle r2. Let's also take a rectangle theta 1, theta 2, and let's look at this rectangle here, r. That's our polar rectangle r. Theta 1 gets mapped over to a line of angle theta. This is angle theta 1. And then theta 2, perhaps it's over here. And this rectangle gets mapped over to this rectangle. So we'll call this rectangle g of r. Now we take the rectangle and we push it through g, and we get this weird polar rectangle thing. Now, if we start at r and increase by delta r, start theta, increase by delta theta, then that's roughly what we're doing here. Think of this as delta r, and then over here is delta theta. What is the area of the output g of r? Last time we already calculated this. This is r delta theta. Last time we calculated this very carefully using geometry. Our goal is to avoid this later. Okay, so we're going to rederive this, and you'll see this r pop out algebraically without using geometry. It's convenient for me to also write this as r times the area of the original rectangle, delta r delta theta. You'll see why in a moment. Here, essentially think of it as if I have an area and then I map it over, then it's multiplied by a factor of little r. So that is our situation. And now let's consider another kind of map, and then we'll unify these together. The second example is thinking about a linear map. It's a linear map where we only have linear terms, okay? No sines and cosines, no squares and other things. And here A, B, C, and D are constants. I know they're interlaced sort of weirdly. You'll see why later. Okay. So as an example, maybe uv is mapped to 3u, 2v, or maybe u plus v, u minus v, and so forth. These are linear terms. We're not multiplying variables together. We're not using transcendental functions and things like that. And here I would like to draw a picture just like the one above. Right? So we start in the UV plane. That's in our UV plane. Then let me draw the line 1 in both of these cases. And then I will shade this. This is my unit square. What happens if we map this over using G to the XY plane? So I want to know what happens to this point 1, 0, and that's this question that's below right here. So if I let the vector r be the output of 1, 0, let's calculate 1, 0. So plug it in here. If u is 1 and v is 0, we get a, b. So a, b is some point. Let me draw a line here and say that this is a. This point is r equals g of 1, 0, which is a, b. Oh, that's that point. And how about this point? 0, 1. That's the next question. So s 0, 1. If we plug it in, we get c, d. This is why I wanted to interlace the A, B, C, and D in that weird way. Okay. C and D. So let me draw another line here, and then say that this point is S equals to G 0, 1, C, D. And the next question, it says if R is this 0, 1 cross 0, 1 rectangle that I've labeled there. Okay. I don't want to label it as R because in the next question I label a different rectangle as R. Okay. So just bear in mind we're thinking about that shaded rectangle. What is the area of the mapped over region? So I need to draw out the mapped over region. Now let me draw it over here. What happens to this line on the right? It becomes this line over here. And it's parallel to this line that I drew earlier. And then this line is parallel to that line. If I can even draw parallel lines. Okay, so this parallelogram is what happened to this unit square. You can think about this 0, 0 is still here. If you put in 1, 1, you will get this point. If you put in 1, 1, you would get a plus c, b plus d. So you add these two vectors and you get that point there. In general, we get grids. Like for instance, if I draw another line here, let's call this A. Then over here, we have another line that corresponds to A. And maybe I'll finish drawing the picture. If you look at part D, you'll see on your page, you'll see that we also want to add in a little bit. So this is A plus delta U. Okay. So then we'll move in the U direction a little bit. Sorry, move in the U direction, yeah, a little bit. So we translate this parallel line. And then also, what if, let's maybe call this line 1 also as B, and then I'll draw another little line here, which is delta V more than 1. It doesn't have to be 1. I just ran out of space here to draw another line. So then here we translate another line here. This is a line that increased by delta V. And then so here, this other rectangle here would be this parallelogram over there. So all the rectangles gets pushed to this, sheared to this parallelogram. You will learn more of this in linear algebra if you take that class. This operation is a shear. You can apply a matrix. This can be written as a matrix, and then you can do matrix transformation on vectors, and you can shear things. I remember a nice joke is like, how do you shear a sheep? You left multiply by the matrix of the form 1k01, and then you'll shear a sheep, because this is a shearing operation. I saw that in my linear algebra textbook when I didn't know the English word shear yet, so I didn't really get the joke. I just thought, yeah, of course, that's how you shear a sheep. And I told that joke when I went to college, and then my friends thought the joke was so terrible they threw me into a pond after politely asking me to hand over my electronic devices and wallets so they don't get wet. So they were very considerate. All right, anyway, so here I want to calculate the area of this parallelogram. And we remember the easiest way to calculate area of parallelogram is using cross products. In order to take cross products, we need 3 dimensions. So let's take the norm, the length of the cross product of A, B, 0. So a third dimension is 0. We don't have a Z component. Cross C, D, 0. And this is equal to determinant of I, J, K, A, B, 0, C, D, 0. We still need to take the norm of that. And this will become still norm. The first component 0, the second component 0 as well. The third component is AD minus BC. The length of a vector like this is equal to AD minus BC. Well, in absolute values. Notice over here I had these norms, length, and over here I have absolute value. But the absolute value, ADBC, another way of thinking about this is determinant of A, B, C, D, and then take the absolute value. So that is the expression we have for now. The next question asks us for the other shaded region. If we push it over, how big is it? So you can work through all this together again, but could you notice that, see, here I have 1, and then it gets pushed to this vector. If we have delta u, it will get pushed to this vector times delta u. Yeah. So this vector is this vector shortened by a factor of delta u. And then, so this vector here is delta u times r. Shifted, of course, but the length is that. And this vector there is delta v times s. So then if we take the cross product, we'll simply get delta u times delta v times r cross s. So then here area is equal to determinant A, B, C, D times delta U times delta V. Everything just here is 1. If we have 2, then it will be twice as much. Yeah, if we have delta U, then it's delta U as much, and so forth. And delta U times delta V, notice that's the area of the rectangle R that we are interested in right now. So again, we can write this as determinant A, B, C, D in absolute values times area of R. And now you see here, area of R pops out again in comparison to here. Area of R pops out, and here in front there's a factor of R, and then below here there's a factor of determinant A, B, C, D. So what we're going to do is see if this pattern holds for even more complicated things. Now let's suppose we have a generic map G. Yeah, it's nice enough for our purposes. And then again, we'll map a rectangle from the UV plane over to the XY plane, and we want to calculate the area, just like before. All right, so here, let me draw the same picture that I've been drawing. Here it's in the UV plane, and let's draw 2 lines. Let's say U1 is A, and U2 is A plus delta U. And then let's draw 2 lines. The first one is V1, the second one is V2. Let's say V1 is B and V2 is B plus delta V. Then we're looking at this rectangle, and I'll mark this point A comma B here, and then we'll map this picture over via G to the XY plane. Now we don't know of specific lines, but we see these 4 lines. I'll draw them sort of generically. So let's say maybe something like this. This is U1, and then maybe something like this, U2. Draw something like this as V1, something like that for V2. So my point is that I'm trying to draw it, sort of curved, and maybe everything is flipped around and everything like that. Now the AB point maps over here, U1, V1 line, and here I'm saying let R be the vector from GAB, that's right here, to GA plus delta UB. So A plus delta U is the U2 line. So here we map U2 and V1. So we go to this point. This is the vector R. And similarly, this is the vector S. Now, let's compute the x component of R. The x component of R is x of A plus delta U, comma B. Yeah, that's this point, minus the x component of that point. So one trick to calculate something like this is to multiply and divide by delta U. So let's write this again. And I'll divide by delta U and also multiply by delta U. Now, if we have this, then I can write this as approximately equal to, what is that? That's the partial derivative with respect to x. With respect to U, with respect to the first variable. Partial derivative of x with respect to u evaluated at a comma b times delta u. I'll drop the evaluated part. So then let me write r is roughly equal to partial x with respect to u times delta u. And the y component, if you have to guess, what would you say? Instead of x, you would get y. Still taking the derivative with respect to u, delta u. So just instead of x here, we have y's, so then we have y's. Now let's also guess what s is. If we look at this, the difference between here is we're going in the direction of u, but what if we go in the direction of v? Then the u's becomes v's. So partial of x with respect to v, delta v, and then partial y with respect to v, delta v. So those are roughly these two vectors. So what we have done is, instead of calculating these vectors, we use the tangent vector. So it's something like this, tangent vector, maybe something like that. So instead, I've drawn tangent vectors. So it's off by a little bit, but if this is short enough, then it's not going to matter too much. Then we're going to do a further approximation. Area of this weird shape, instead of using that shape, we'll use the parallelogram that's formed by these two vectors. So here's two approximations. I could have used the actual r and s vector to write a parallelogram. That would already not match this weird shape. Okay? But now I'm using approximation of r and approximation of s for the weird shape. So this is a lot of approximations. This is partly why I couldn't get you to do this yourself. Yeah, because you wouldn't know how much approximation you could use. If I ask you for the exact amount, you can usually calculate it. But if I ask you for approximation, you're like, what should I approximate it as? So here, this further approximation to calculate the area spanned by these two vectors. We've already done this several times. So let me directly write it out. We've done it twice on the other page. We get a determinant of this vector followed by this vector. You could add the 1 and the zeros and then take the ijk and then calculate it, but we've done that already. We know it's going to end up like this. And furthermore, we can pull out the delta u and the delta v's. And if we multiply delta u and delta v, we get the area of r to start with. So then we can pull this out. This is exactly equal to the determinant partial x partial u partial y partial u partial x partial v partial y partial v. That determinant, the absolute value, it could be negative and just off by a sign. This one, if we flip it around, it might be negative, times the area of r. Again, we get the area of r to come out from the delta u and delta v. So here, this expression is the one that keeps popping up. So we're going to give it a name, and then that's going to be part of this theorem. So now we're ready. We see where this came from. We're ready to write this theorem. So we have a nice map, and we have a continuous function. What we would like to do is to calculate the integral of f of xy. And usually we would write dA, but because everything is area, I'm going to write dx dy, but that's dA. I want you to be aware that we are in the xy plane right now. I'll leave this blank for now. The theorem says that's equal to another double integral. And here we're going to use u's and v's. So I will evaluate x as a function u and v, y evaluated as u and v. Think last time we wrote r cosine theta here and r sine theta there to write everything in terms of r's and thetas. And then here, think last time when we used polar coordinates, we had an r here. That's this thing. And that thing, there's a shorthand notation, so I'll write it this way. xy on top and uv below. And then we'll have du dv. And you should treat this whole thing as dA. So we have two double integrals. Both of them are dAs, integrating with respect to area. One of them is in the xy coordinates, and the other is in the uv coordinates, and we have a change of variables factor right here. Then finally, we also need to write the domains here. Okay. So think about this carefully. If you look at the picture above, which I can't point to right now because it's too far away, we're mapping from the uv plane to the xy plane. So on the uv side, we can write some kind of domain D, and then we map it using G to get it in the xy plane. Okay, so this seems a little backwards, but think about it one more time now that you've seen it. Yeah, we start with a region, not necessarily a rectangle anymore. Okay, some kind of generic region in the UV plane, and then we map it using G to the XY plane. So that's the direction that we're going. And let me formally write this out as a shorthand. Okay, so I continue with this English sentence, then this, where I'm going to define that. So this x, y, u, v. This is known as the Jacobian. And it's given by this formula that we had above. So you can also write the Jacobian as Jac G, and also with this notation. Different books like to use different notation. And then equal to some kind of determinant without the absolute value. Okay, the absolute value is already here. Yeah, so we don't need the absolute value. I just need the thing inside the determinant. And usually, for other reasons, people will flip this matrix around, called transpose this. So it's the top row have x's. Okay, so I'm exchanging these two positions. But of course, if I write out this determinant, you'll see that it doesn't matter. So the determinant is the multiply the diagonal together and then subtract the product of the other diagonal. So you can see that if we didn't transpose it and didn't exchange these two, we'll still get the same answer here. So it doesn't matter if we transpose it or not. But then here, these are, when you take linear algebra, or in linear algebra, when people deal with this a lot, usually they have column vectors, and they write vectors as columns instead of rows. We've been writing vectors as rows, but they like to write vectors as columns. So that's just a notational convenience and what is this called? Custom. So convention. Yeah. So I flipped that. But again, it doesn't matter. Oh, this is a complicated looking theorem. Let's give this a try. So here is the polar coordinate map that we saw in exercise 1 on the previous page. Well, we saw it last time. Let's calculate its Jacobian. So Jacobian of G is equal to, let me write it out using this notation. So we have x, y, and then below, instead of uv, we have r theta. And what we have is we have a determinant of partial derivatives. Now, we have the x, which is r cosine theta, and we take the derivative. Let me write out the derivative. This is with respect to the same thing, with respect to r. And then we'll write r cosine theta here, and r sine theta here. Then we'll also have the term with respect to theta, and again, r cosine theta, r sine theta. And this is equal to, let's write determinant, and let's calculate. And actually I think taking the derivative with respect to r for these is, I would do it column by column, because it's something, and if you're in the mindset of taking derivative with respect to r, it's faster. So you get cosine theta and sine theta, and then now you can switch mindset to take the derivative with respect to theta. So that's negative r sine theta and r cosine theta. That determinant is equal, so cross multiply, we get r cosine squared theta, and then minus the product, which has a negative sign in it, so plus r sine squared. And of course, your favorite identity gives you r. And so then what this theorem says is then, so dx dy on this left side is equal to r dr d theta. Yep, so that is what this theorem says. We saw the theorem in action on polar coordinates, which we already know the answer of. Now let's try it on a map that we don't know how to use without the theorem. So here we're integrating, we are trying to compute this integral. Here I've written dx dy, but usually you would just see dA, and d is bounded by certain things. And the idea is that we're going to use a map. Why? Well, we'll see in a moment. Okay. So here, let me draw out the UV plane. I don't know what that region is yet, but then I know that we're going to map it using G. And now let me first trace out the XY plane and the region in here. Here, D is bounded by y equals x, so let me draw that out, y equals x. I know you want to draw it out slanted more, but I also see y equals 2x. I'll draw that twice as tall, y equals 2x. So figure not drawn to scale, but drawn to scale in that sense. Well, y equals 2x. And also the line y equals 3 minus x and y equals 6 minus x. So minus means it's slanted down. One starts at 3 and the other starts at 6. Y equals 3 minus x. This one is y equals 6 minus x. And so then D is bounded in here. And by the way, I'm going to draw it like this. Usually when I shade things, I shade, sort of slantedly, but I just want you to see that if we had been wanting to integrate this, these lines will have a lot of different weird bounds. Yeah. Sometimes the left side would be using the y equals 3 minus x line. Sometimes it'll be the y equals 2x line. And for the right side, it'll be y equals x and sometimes switch to y equals 6 minus x. So how you would integrate this without changing variables is that you would split this region up into maybe 3 pieces. One piece down here, one piece in the middle, and one piece up there, and then integrate those 3 things separately. Or you could vertically, you can split like this, then you'll have one piece over there, one piece in the middle here, and then a third piece on this side. So you'll need to calculate 3 double integrals. But perhaps we can simplify this. So let's look at this region. How could we describe this region? Here, over here, I can see that x plus y is, this is x plus y equals to 3. And this is x plus y equals to 6. So we're in between these 2 lines, so x plus y is between 3 and 6. Now what is x plus y? X plus y is equal to, we have this map given to us. We don't know why someone would give us this map. Where did that come from? I'll show you in a moment, or maybe in 3 moments. But for now, let's use that. So x is u over 1 plus v, and y is uv over 1 plus v. And so if we add that together, we get u plus uv over 1 plus v. In other words, u times 1 plus v over 1 plus v. In other words, u. So then from this calculation, we see that the region has a simple description of u between 3 and 6. Now let's hope the y equals 2x and y equals x thing is just as easy. So over here, we see that y divided by x is between 1 and 2. This line is y divided by x is 1. This line is y divided by x is 2. So let's calculate y over x. Well, we should be able to just see this directly. Yeah, this thing divided by that thing is just v. Maybe I'll write it out so you know where this is coming from. uv over 1 plus v divided by u divided by 1 plus v. So that's equal to v. So in other words, we have that 1 is less than v, u is between 1 and 2. So now I can come back and draw over here, very simple region, 1, 2, and then over here is 3 and 6, and that's the region, which I'll call R. So it turns out to be a nice rectangle. So this integral was not complicated because the integrand is complicated. Sometimes we'll see that, but it's complicated because the region is shaped weirdly. And if you think back to polar coordinates, that's often the case. We have regions that look like circles, and that's easy to describe in polar coordinates, but much more complicated to describe in rectangular coordinates. Here, this weird quadrilateral, it's not even, oh, it is a trapezoid. Okay, so this trapezoid is hard to describe in rectangular coordinates, but it's very easy to describe in UV coordinates. Maybe we can call this trapezoidal coordinates, where in trapezoidal coordinates, the rectangles, trapezoids are rectangles. So I want to emphasize one more time that this map seems to be going backwards. We start here, and then we have this map, and we have to reverse engineer what the region R is, because we're given this region is D. We are given this region, and we have to go backwards to find that other region. So this is the first step to figure out this region. And then what we would do now is to calculate, if we want to use the theorem, we need to calculate the Jacobian. So this part is straight calculation, and I'm sure you can do it. The Jacobian, where we need to calculate a bunch of partial derivatives. And let me, instead of writing determinant, I will write a bar now for determinant. So dx du, and then or dy du, and dx dv dy dv. This is equal to, so let's take this thing, x and y, and take the derivative with respect to u. So let's 1 over 1 plus v, and v over 1 plus v. Oh, that's the derivative with respect to u. Now we also have to take the derivative with respect to v. Oh no, this is, no, this thing will have negative u 1 plus v squared. This one, we need to use quotient rule. Alright, I guess I didn't leave enough space there for quotient rule, but I'll write it down here. So the bottom is 1 plus v squared. The top is the derivative of the top times the bottom minus the derivative, the top times the derivative of the bottom. Oh, let's multiply this out. This is equal to, we multiply those things together. Can we simplify this? U plus uv minus uv, so that's just u. Yeah. So 1 over 1 plus v times u over 1 plus v squared. So here's u plus uv minus uv. Minus, and then product of these two, but because there's a negative, so that becomes plus. Then we have v 1 over 1 plus v times u over 1 plus v squared. If we factor this out, we get equal to 1 plus v cubed on the bottom. And the top is u plus uv. So instead of writing u, I'll factor out the u, so then it's 1 plus v on top. So then I can cancel out one of the 1 plus v's, and we get u over 1 plus v squared. No, that's the Jacobian. Now that we have the Jacobian, we are ready to proceed. So the double integral over d of x plus y dx dy is equal to, by our change of variables formula, a double integral over the rectangle, and then we need to write x plus y in terms of u and v. Well, we already figured that out. X plus y is equal to u. Here, x plus y is equal to u. So here I can write u, but I'll note that this is x plus y. That's the integral we're trying to calculate, x plus y. And then dx dy, that turns into the Jacobian. So it's the absolute value of u 1 plus v squared. So this is a Jacobian, and we need, the formula says it's the absolute value of the Jacobian. And then du dv. So now By the way, our u's and v's are positive, so that I can drop that absolute value sign. So let's write this as iterated integrals of u squared over 1 plus v squared du dv, and u, we had drawn this picture over here. U is between 3 and 6, and v is between 1 and 2. U is between 3 and 6, v is between 1 and 2. And this is again one of those special integrals that can be factored into just u's and just v's. So then we have two single variable integral problems, u du times integral of 1 over 1 plus v squared dv. That at this point I don't really want to do it, but this is easy enough, so I'll write it out. U cubed over 3 evaluate from 3 to 6, and then times, here the integral is negative 1 over 1 plus v evaluated from 1 to 2, and that's equal to 21 over 2. Oh, if you want, you could chop the original region into 3 pieces and then use usual rectangular integration to see if you get the same answer. I would say that's unnecessary. So now, as promised 3 moments ago, I would like to show you how, we're done, but I want to show you how anyone would come up with something like that. So after we've done these, well, suppose we have this. 3 is between x plus y is between 3 and 6, and y over x is between 1 and 2. So we don't know the relationship between x and y and u and v yet. Suppose we don't have this map. How would you come up with it? Well, here you see this region between 3 and 6. Maybe let's call that u, and say u is x plus y. Oops. Yeah, u equals x plus y. And then because we see this y over x as something that's between 1 and 2, maybe let's call that v. I know that's our conclusion, but suppose we don't have those expressions. So we would simply say that we want these two things. And then once we have these, we can solve for x and y in terms of u and v. So how would you do that? Well, here u is equal to x plus, what is y? Y is xv. Here y is equal to xv. So here we can write xv. Then might as well factor out x and get 1 plus v. And so at that point you can solve for x. X is equal to u over 1 plus v. And then y is equal to x times v. So if we put that in here, we get uv over 1 plus v. And that's the map G that we were given. So if we didn't give you the map, you can find the map yourself. For this first exercise, I wanted to give you the map. In your homework, sometimes you will be given maps and sometimes you won't, but you can find the map yourself. I remember our motivation for doing all this was to get spherical coordinates, the formula for spherical coordinates. So I need to tell you what happens in 3 dimensions. Here if G is dependent on 3 variables, vw, and then it outputs 3 variables x, y, and z, then Jacobian is defined as, well, what you think it should be. Yeah, the x, y, z with respect to, take the derivative with respect to u, with respect to v, with respect to w, and then calculate the determinant that way. And then dx dy dz will be the same as du dv dw multiplied by the absolute value of the Jacobian. So here, the 7th exercise, well, I suppose there's nothing in the 6th exercise. Right? The 7th one is a bonus because I don't actually want to calculate these things and the 9 partial derivatives, right? But you could. And if you did that, then you would prove the spherical coordinates change of coordinate formula that we saw last time. Instead of doing this, I thought perhaps we can just do this on Mathematica. So let me show you Mathematica. Yeah. And I posted this file on Moodle so you can look at it. Okay. So suppose x is, this is spherical coordinates, rho, sine phi, and then cosine theta, sine theta, and z is this. So let me evaluate this. Yeah, so we get those things. And now let me take the partial derivatives and I'll display that in matrix form so you can see it. Now this is the Jacobian matrix, and to calculate the Jacobian, so those you can do yourself. Yeah, and in fact you can probably verify this just visually, how to make sure that we did do this correctly. And then the Jacobian is we take the determinant of that matrix, determinant, and we get this really long looking thing. But we can simplify it. Yes, if we simplify it using sine squared plus cosine squared equals to 1, then we get rho squared sine phi, which is the formula that you saw before. So indeed, this is what we have. And so what we did just now allowed us to calculate the change of basis formula for spherical coordinates without using any geometry. You just plug those things in algebraically and out comes the formula. Now there's one more part on the worksheet, that's question 8. What happens in 1 dimension? We went from 2 dimensions to 3 dimensions. Let's go back to 1 dimension. I labeled this as bonus because I never have time for this in the first class, right? And sometimes I would talk about it on the second day. But regardless, since it's a video now, I do have time for this. So what is G? G, well, G is in terms of the variable U. That's it. Yep. So earlier we had UV, and up there we had UVW. Here it's just U. So then its output is x of U, x in terms of U. Then what is the Jacobian? Jacobian of G. That's the partial x with respect to U. Actually, that's not a partial derivative. Yeah, if x is a single variable function, that's just x prime. Maybe let's write this as G prime U. And so then what we have, the theorem gives us that dx is equal to the absolute value of G prime U du. Now, if you do things correctly and you can drop the absolute value bars, this is essentially what we have learned is integration by substitution that you learned in Calc 1 or Calc 2. This is not exactly how we usually write it, but it's very, very close. So I want to show you that what we did today is an extension and generalization of integration by substitution. Okay, so that's it for today.